Hello. I just want to give a little brief review of this PowerPoint slide set that talks about managing batteries and understanding batteries that are used in weather station applications. And I'm going to use an analogy of this Coke bottle, which has a nice shape of being small at the top, big at the middle, and small at the bottom again. So first off, let's look at some data from some real stations to see how data typically looks. So if we had an ideal station and it was reporting its voltage and everything was perfect, it may well report that the battery was at 100% charge. And this would be, for many days perhaps. This is an actual station over a period of a month. And what we see is that it's always reporting 100%. One thing about that is it's not reporting voltage, it's reporting the apparent level of charge. And in this case, the charge is actually above their threshold. So even though, in fact, the voltage is just changing a little bit between day and night, it's only reporting that the battery appears to be fully charged. This would be a properly working station. Now, if we look at a station that has been getting some attention from our maintenance team, we see that here's a station where with the first set of batteries, they were seeing some drop in voltage, and they said, oh boy, that needs to be replaced. So they replaced a set of batteries to set number 2. Those also failed. They put in another set 3, that failed, and then set 4 finally failed. And this was a very expensive undertaking to go to the field 4 times to replace batteries. What was going on here? Were these bad batteries? No. This was a station where either the solar panel was not charging adequately or the instrument was drawing more power than the solar panel could come up with. There are some hints in these data, and we see that the fluctuation indicates that each day it was getting some extra charge, but it was losing a little bit more charge than it was gaining. This suggests that this was a faulty sensor head, or in some way a system that was drawing more power than the solar panel was able to charge. So not a bad battery set. These are data which show a problem with either the data logger or the sensor head. And so this would not be a case of bad batteries. Here, I want to show you a case that's more likely to be bad batteries. What happens when a battery goes bad? When a good battery goes bad, what it means is that the chemistry has changed to the point where it no longer can store much energy. So all of a sudden, it has very, very little energy storage capacity, meaning that in a typical day of sunlight, if it's sunny and the solar panel wants to store a lot of charge, it'll go up dramatically because it's like a tiny little vessel, and you put a little bit in it, and the level, it gets full. So if we look at these data, we see that there's these big swings from low to high to low to high. And that's indicating that the battery has so little capacity left that it both charges very fast and discharges very fast. This is a classic example of what would be indicative of a bad battery. Let's just kind of review a little bit what we're talking about when we talk about voltage and current and power and energy. And it's good to use the analogy of a dam. And here we can see a reservoir in the upper right where we have this stored energy, and that's going to be the height of the amount of water times the volume of the water. So that's a stored energy. The height of the water is going to be our analogy for voltage. The higher the voltage, the more energy per unit water or per unit electron that you get out of a battery. So high voltage batteries have more energy per electron. And then the flow through the turbines would be the current. And that's how many, in this case, liters of water, or in a battery, how many electrons are flowing out of that battery. The rate at which power is delivered is given in watts, and that's going to be the voltage times the current. That is to say, the height of the water column times how much flow there is. And that's telling you how much power is instantaneously being delivered. But the energy, and that's going to be power over time, is going to be measured in watt hours. And that's to say, how much energy could this battery deliver? So you could have this same battery deliver 1 watt for 100 hours or 100 watts for 1 hour. It's the same battery, the same amount of total energy stored, okay? So it's watt hours, and you'll see those terms, okay? So that's the basic notion, that we have the energy per electron, that's volts, the number of electron, that's amps, the volts times amps gives us the amount of energy that's going instantaneously, and then if you add that all up, the watt hours is how much total work can the battery do. Now, there's very little math that you really need to know here, and this is, in fact, more than you need to know, but let's just review the very, very simplest parts. One of them is called Ohm's law. That is, if you have a voltage and you have a resistor, something that uses energy, that could be a weather station. So you have a weather station that acts like a big resistance, and a battery that's providing the voltage. The current is going to be related to those two, that the voltage is equal to the current times the resistance. Okay? So that allows you immediately to say, what is the effective resistance of my station? Well, I could just measure the voltage of the batteries and divide it by the current that was being drawn, and that would be the effective resistance of that station, for example. On the other hand, the power, that's the instantaneous amount of energy being consumed by that station, let's say, is the current times the voltage, like we talked about before. And so that's the power equation. The upper one's Ohm's law, and we can put them together and we can say that, that the power is equal to V squared over R. So that's a very common way to see the power. If you knew the resistance and you knew the voltage, but you didn't know the current, this is how you could determine the rate of power consumption. And these are just kind of basic equations for electricity. Okay? Now, let's look at this in kind of the context of a real battery. Here is a 12-volt, 7 amp-hour battery. So the amp hours is how many electrons it holds. It holds 7 amp hours worth of electricity, okay? And that would be the volume of the reservoir. The voltage is the energy per electron. That's the depth of the reservoir. And so how much energy is in a 12-volt, 7 amp hour battery? It's the product of the voltage times that current times time. So it's going to be 84 watt hours. It'll provide 84 watt hours. So if you had a light bulb that burned up 80 watts, it would drive that light bulb for about 1 hour. On the other hand, if you had a light bulb that only burned 20 watts, it would drive it for about 4 hours, okay? Now, when we use a solar panel, it's really important to understand a little bit about what that means. And so let's just go over some very basics of solar panels. Here I'm looking at a 6-watt solar panel, very typical. And first off, we should find out what 6 watts means. Watts, we know, is an instantaneous delivery of energy. And so when they rate a panel, that is if you had it in the middle of the day with the sun right over your head and you have the panel pointing directly at the sun. That's the maximum power you'd expect to see ever out of that panel. And so if I want to know how much energy that panel will produce in a day, I need to know how many hours of sunlight that would be equivalent to those right overhead. And that's called the insolation. And so typical environments, like around equatorial regions, on a sunny day, you might have 6 hours of insolation. Here in the northern hemisphere during the winter, you might be 3 or 2 or less if it's cloudy. And in the summer, you might even get more, like 7. Okay, so you're going to see then that the insolation, which is the equivalent number of hours of full sunlight, times the rating of the panel, gives us the expected amount of energy off of that panel. So if the insolation was 5 hours and it was a 6-watt panel, that would give us 30 watt hours per day. Now remember, that battery we just saw had 84 watt hours of capacity, meaning that if there was nothing hooked up to take any energy except the solar panel feeding the battery, it would take almost 3 days to charge that battery. Clearly, if a weather station was drawing energy off of that same battery, it would take even longer. But you get an idea about how we size a solar panel is related to how big the batteries are and how much the energy we need, and the energy we would measure in watt hours per day. Clearly, the angle of the sun relative to the panel is very important. And so many of the panels we'll see that are used in weather stations are often at 45 degrees. And that's because if you were anywhere on average on Earth, 45 degrees is a pretty good angle because the sun, if you have it pointing in the direction of the sun, that is the average annual angle that the sun is at for mid-latitudes. Now at the equator, then you may well prefer to have the panel flat even. But the point here is that when the panel is at a steep angle and the sun's coming down parallel to it, you'll have no generation. The other piece I want to talk about with panels is shading. It turns out that most panels, if you shade any tiny fraction of the panel, they lose the ability to generate any energy. So watch out if you have a leaf or dirt in the corner of the panel, or if there's a shadow of a tree that goes over the panel, all the time, if there's any shading at all, you can assume you'll have zero production of electricity from that panel. So any sort of shading, any dirt around the perimeter of the panel can have a much more dramatic effect on the rate of charging than you'd ever expect. Now, batteries that we use are hooked up in two basic ways. One might be in parallel and one might be in series. Parallel means that all the batteries, and looking at the left-hand image here, all the batteries have their plus ends and their minus ends hooked up to the same set of wires. What you end up with then is the basic native voltage of the battery. Let's say it was a 1.2 volt battery, then you would have 1.2 volts across that whole package of parallel batteries. But if each battery had 2,000 milliamp hours of stored electricity, you would get 8,000 milliamp hours taken together, which is the sum of all of those batteries. On the other hand, if you hooked the plus end of one to the negative end of the other and do them in a chain, essentially, that's what's called series. Now you're going to add the voltages between each battery. So it'll be 4 times 1.2 volts will be 4.8 volts. But the current will be just the number of electrons from any one of those batteries. So what you can see is if we calculate the watt hours, they're exactly the same in both cases. Watt hours are amp hours times voltage, both the same. You don't win any energy by changing these setups. What you do get is a higher voltage. Now, one of the dangers of a series circuit like we see is that if any one of those cells stops functioning completely, then you can lose all the system and it won't transmit any energy. So one cell might be enough to ruin your entire system. In the parallel, if one cell shorts out, it will draw the energy from all the cells. So in both cases, there are failure modes where one bad battery can cause a problem for the entire system. This is very important for weather stations because you might say, oh, I think this is a brand new battery. I've got 4 new batteries and 1 old battery. That may give you only the performance of the worst battery. So this is why we have to test every battery, regardless if it's in a parallel or series configuration. We really want to test every battery. And testing batteries, luckily, is getting easier and easier. One of the circuits that we really recommend is this ZB2L3, and it's made broadly. You can get these for about $3 each. And what it does is it takes a fully charged battery and it dumps the electricity through these 2 resistors, or 1 or 2 resistors, depending on how you set it up. It dumps it through the resistor and reports back to you what the amount of total current that went through it. So it tells me how many amp hours I can get out of that battery. So I can test every battery and see if it's rated at 1.2, or let's see, the last one was rated at 2 amp hours per battery. Then if I only get 1.5 amp hours, then the battery has lost a quarter of its capacity. And so we really recommend that you test every battery every time you go to the field. What that requires then is to charge the battery up fully in your normal charger, then put it in the ZB2L3 discharger, let it discharge fully, look at the amount of amp hours that it generated, and say if it's above your team's threshold for a functional battery. I would say that if it's not more than 3/4 of the rated value, you should put that into a category of batteries that are not useful for weather stations. We need to have very high-performing weather stations, okay? So we have to choose to set up the ZB2L3. We have to set up the resistors. So we have to choose the resistors. And I'm suggesting that for a 1.2 volt battery, like our stations employ, that we'd be looking at approximately half an ohm would be the size bat. And then that half ohm resistor should be a 5-watt resistor so that it can dissipate the energy without burning up, okay? If you were using, this system could be used for higher voltage batteries as well, but you have to then adjust the resistor to make sure you still don't go over 5 watts, okay? Now let's get back to our Coca-Cola bottle. And so I want you to understand that the voltage out of a battery does not tell you necessarily how much energy is left in the battery. And any of you who've had cell phones for a while will know that as the cell phone ages, what used to look like 50% of my battery left is all of a sudden very little. And so a battery is kind of like a Coke bottle. That is, when you have it charged completely to its top capacity and you start using energy, the initial voltage will drop pretty quickly until it reaches the base chemistry level of that battery. Then it'll hang out pretty much at that target voltage until it runs out of electricity, and then it'll fail. And so that's kind of like drinking a Coke bottle. The top is very narrow. Take a sip, it goes down quite a bit. In the middle of the Coke bottle, it doesn't go down so fast because it's quite large. And at the end, they make the bottle small again, and oh, where's all my Coca-Cola? So what we see then is that the battery discharge curve and your Coca-Cola discharge curve looks like this in time. As long as you're consuming a constant rate of electricity and you're not recharging in net, then as you're discharging the battery, this is what a discharge curve looks like. It has a small bottle cross-section at the top initially, then a bigger, then small again. And so the voltage goes down a lot early, then it goes flat, then drops. That each day it charged and discharged, and what we're getting is a slope on that overall curve showing us that it's in net discharging, and that slope can tell us how much energy is being lost per day. And so we can go through the math on that, but the point is that if they're using more energy than you're providing, it's going to go down in voltage over time. Okay. And we can then, this slide is really just for those of you who really want to dig into understanding the nature of what that slope tells us. And honestly, it's cool, but it's not necessary. I want you to understand the basic principles more than the math here. What I would recommend is that you use something like this decision tree, where we say, gosh, we start at the top, batteries are dying. And then we say, well, the batteries are dying. Does it look like bad batteries? How do we know if it's bad batteries? Big daily swings, huge daily swings in voltage or percent charge. If you see those big daily swings, whoops, bad batteries, get some new batteries. If it's not bad batteries, then go down and say, well, is it a problem with the solar panel, or is it that that my instruments are using too much electricity? So if it's the solar panel, you'll want to clean the panel and move it into full sun. If it's not, then you're going to go through a set of further checks. So making a little flow diagram to take us through the steps of what is causing our problem and how we might resolve it is a fundamental piece of having a field strategy. And this then tells you what you need to bring to the field to be able to resolve any power problem. So in summary, what I want to come to is that most of the energy problems we've been seeing in Tomo are not due just to bad batteries. Many times they're due to either a dirty solar panel or the electronic system drawing too much power. So the overarching result of that is that we don't have as much power as we need, so the supply is insufficient. This can also come from poor cell phone communication. That is to say, if our cell phone tower is demanding that our station call over and over and over, that will use a lot of energy. Even if the solar panel is good and the electronics are working fine, the calls to the cell phone network can be very expensive by way of energy. And the funny thing is, we've seen this happen even when you're very close to a cell phone tower. So you really have to look at your station. How many calls does it have to make to get a good connection? Okay. In general, batteries need to be changed about every 3 years. If you're experiencing more frequent failures, there's likely some other problem at play here. It's probably not the batteries alone. Finally, I want you to really remember that you can get fancy little meters like this that say that they will test your batteries. A little battery tester, your universal battery tester. Just throw this right in the garbage. Why? Because it tries to tell you the capacity of the battery based on a quick little measurement. But that never will be accurate with respect to what the real capacity of that battery is. The only way to get the real capacity is take it all the way from a full charge to full discharge and see how many amp hours are in that battery. Thank you very much for your attention today, and I would be happy to answer any questions. Again, John Selker at Oregon State University.